Hello everyone, my camera's off, and welcome back to Teach Astronomy. My name is Victoria, but you can call me Vicky. And today is Monday, which means we're doing book chat. It looks like I'm a little loud. Gotta turn myself down a little bit. I think that should be better. Hope everyone's doing well this Monday morning. Thank you for being here a little early like we did last week. It's working out a lot better from my schedule. I hope it works well for your schedule as well. Hi, Lynn Jersey. Hi, Student McLeod. Happy Chapter 10 Day. As Student McLeod said, we're reading Chapter 10 today of Dreams of Other Worlds. And this chapter is all about the Hubble Space Telescope, which should be really fun. And let me know. Last week we were having an issue with the microphone. It was making like a weird clicking noise. Let me know if you can hear that. And if you can, we will mess around with stuff. It doesn't look like it's showing up on my, it sounds good? Okay, cool. Because it didn't look like it was showing up on my stream, so great. Well, I guess we will just jump right into it then. Let's learn about Hubble. All right. HST, the universe in sharp focus. Above all scientific projects, the Hubble Space Telescope encapsulates and recapitulates the human yearning to explore distant worlds and understand our origins and place in the universe. Its light grasp is 10 billion times better than Galileo's best spyglass, and many innovations were needed for it to be realized. Complex yet reliable instruments, the ability for astronauts to service the telescope, and the infrastructure to support the projects of thousands of scientists from around the world. The facility and its supporters experience failure and heartache, as well as eventual success and vindication. Hubble's legacy has touched every area of astronomy, from the solar system to the most distant galaxies. In the public eye, it's so well known that many people think it's the only world-class astronomy facility. In fact, it operates in a highly competitive landscape with other space facilities and much larger telescopes on the ground. Although it doesn't own any field of astronomy, it has made major contributions to all of them. It has contributed to solar system astronomy and the characterization of exoplanets. It has viewed star birth and death in unprecedented detail. It has paid homage to its namesake with spectacular images of galaxies near and far. And it has cemented important quantities in cosmology, including the size, age, and expansion rate of the universe. Ranked by size of the mirror, Hubble wouldn't make it into the top 50 largest optical telescopes. Its preeminence is based on three factors associated with its location in Earth orbit. The first is liberation from the blurring and obscuring effects of the Earth's atmosphere. Ground-based telescopes typically make images far larger than their optics would allow, because turbulent motion in the upper atmosphere jumbles the light and smears out the images. Hubble gains in its sharpness of its vision by a factor of 10 relative to a similar-sized telescope on the ground. Earth orbit also provides a much darker sky, which affects the contrast and depth of an image. The difference you might see in going from a city center to a rural or mountain setting is only part of the story. Natural air glow and light pollution affect even the darkest terrestrial skies. A vacuum can't obfuscate. The last feature of a telescope in Earth orbit is its ability to gather wavelengths of radiation that would be partially absorbed or even quenched by the Earth's atmosphere. Hubble has taken advantage of this by working at infrared and ultraviolet wavelengths. The Hubble Space Telescope, HST, is well into its third decade of operations, and it's easy to take for granted the beautiful images that are released almost weekly. But it was not an effortless journey for NASA's flagship mission. A long and bumpy road. In 1946, Yale astronomy professor Lyman Spitzer wrote a paper detailing the advantages of an Earth-orbiting telescope for deep observations of the universe. The concept had been floated even earlier, in 1923, by Hermann Oberth, one of the pioneers of modern rocketry. In 1962, the U.S. National Academy of Sciences gave its imprimatur to the idea, and a few years later, Spitzer was appointed chair of a committee to flesh out the scientific motivation for a space observatory. The young space agency NASA was to provide the launch vehicle and support for the mission. NASA cut its teeth with the orbiting astronomical observatory missions from 1966 to 1972. They demonstrated the great potential of space astronomy, but also the risks. 2 of the 4 missions failed. We've already encountered Spitzer since he gave his name to NASA's infrared-grade observatory. Spitzer worked diligently to convince his colleagues around the country of the benefits of such a risky and expensive undertaking as an orbiting telescope. After the National Academy of Sciences reiterated its support of a 3-meter telescope in space in 1969, NASA started design studies. But the estimated costs were $400 to $500 million US, and Congress balked, denying funding in 1975. Astronomers regrouped. NASA enlisted the European Space Agency as a partner, and the telescope shrunk to 2.4 meters. With these changes, and a price tag of $200 million US, Congress approved funding in 1977, and the launch was set for 1983. More delays followed. Making the primary mirror was very challenging, and the entire optical assembly wasn't put together until 1984, by which time launch had been pushed back to 1986. The whole project was thrown into limbo by the tragic loss of the Challenger space shuttle in January 1986. When the shuttle flights finally resumed, there was a logjam of missions, so another couple of years slipped by. Hubble was launched on April 24, 1990, by the shuttle Discovery. A few weeks after the systems went live and were checked out, euphoria turned to dismay as scientists examined the first images and saw they were slightly blurred. The telescope could still do science, but some of the original goals were compromised. Instead of being focused into a sharp point, some of the light was smeared into a large and ugly halo. This symptom indicated spherical aberration, and further in-flight tests confirmed that the primary mirror had an incorrect shape. It was too flat near the edges by a tiny amount, about 1/50th of the width of a human hair. Such was the intended precision of Hubble's optics that this tiny flaw made for poor images. Hubble's mirror was still the most precise mirror ever made, but it was precisely wrong. The spherical aberration problem may be ancient history and in the rearview mirror now, but at the time it was a public relations nightmare for NASA. Its flagship mission could only take blurry images. Commentators and talk show hosts lampooned the telescope, and David Letterman presented a top 10 list of excuses for the problem on The Late Show with David Letterman. More seriously, the episode became fodder for case studies in business schools around the country. The fundamental error was the result of poor management, not poor engineering. The Space Telescope project had 2 primary contractors, Perkin-Elmer, who built the optical telescope assembly, and Lockheed, who built the support systems for the telescope. There was also a network of 24 secondary contractors from the aerospace industry. The mission was jointly executed by Marshall Space Flight Center and Goddard Space Flight Center, whose relationship involved rivalry and was not always harmonious, with overall supervision from NASA headquarters. Complexity of this degree can be a recipe for disaster without tight and transparent management, and clear communication among the best technical experts. When the primary mirror was being ground and polished in the lab by Perkin-Elmer, they used a small optical device to test the shape of the mirror. Because 2 of the elements in this device were mispositioned by 1.3 millimeters, the mirror was made the wrong shape. This mistake was then compounded. 2 additional tests carried out by Perkin-Elmer gave an indication of the problem, but those results were discounted as being flawed. No completely independent test of the primary mirror was required by NASA, and the entire assembled telescope was not tested before launch because the project was under budget pressure. Also, NASA managers didn't have their best optical scientists and engineers looking at the test results as they were collected. The agency was embarrassed and humbled by the failure. Their official investigation put it succinctly, quote, "Reliance on a single test method was a process which was clearly vulnerable to simple error." End quote. In this way, a multi-billion-dollar mission was hamstrung by a millimeter-level mistake and the failure to do some relatively cheap tests. In the old English idiom, penny wise, pound foolish. The propagation of a small problem into a huge one recalls another aphorism from England, where a lost horseshoe stops the transmission of a message, and the result affects a critical battle. For the want of a nail, the war was lost. That's the end of that section. I'm going to grab a little bit of water. How was everyone's weekend? Here in the U.S., next weekend is going to be Memorial Day weekend, which is very exciting. I am, surprisingly, I was able to get off from my other job, and I will be going to Tucson to record for my podcast and see some friends and stuff. And I am super excited. We didn't think we'd be able to do it because we weren't sure if everyone would be vaccinated. But since we are all vaccinated, it's happening. It's very exciting. You had your 40th wedding anniversary on Sunday. Congratulations. That's amazing. I hope you guys did something fun. That sounds lovely. All right, let's see. A telescope rejuvenated. In fact, NASA had lost a big battle, but they weren't yet ready to concede the war. With Hubble working at part strength, the agency immediately began planning to diagnose and correct the problem with the optics. Although a backup mirror was available, the cost of bringing the telescope down to Earth and relaunching it would have been exorbitant. It was just as well that the telescope had been built to be visited by the space shuttle and serviced by astronauts. The instruments sitting behind the telescope fit snugly into bays like dresser drawers, and they could be pulled out and replaced with others of the same size. It also helped that the mirror flaw was profound but relatively simple, and the challenge was reduced to designing components with exactly the same mistake, but in the opposite sense, essentially giving the telescope prescription eyeglasses. The system designed to correct the optics was the brainchild of electrical engineer James Crocker, and it was called COSTAR, or Corrective Optical Space Telescope Axial Replacement. COSTAR was a delicate and complicated apparatus with more than 5,000 parts that had to be positioned in the optical path to within a hair's breadth. Installing COSTAR raised the difficulty level of an already challenging first servicing mission that was planned for late 1993. 7 astronauts spent thousands of hours training for the mission, learning to use nearly 100 tools that had never been used in space before. They did a record 5 back-to-back spacewalks, each one grueling and dangerous, during which they replaced 2 instruments, installed new solar arrays, and replaced 4 gyros. This last fix was needed because of the disconcerting tendency of Hubble's gyros to fail at a high rate, in a way never seen in lab testing. Working without gyros, the telescope could not point at or lock onto a target. Before leaving, the crew boosted Hubble's altitude, since 3 years of dragging in Earth's tenuous upper atmosphere had started to degrade the orbit. The first servicing mission was a stunning success. It restored the imaging capability to the design spec and added new capabilities with a more modern camera. It also played significantly into the vigorous debate in the astronomy and space science community over the role of humans in space. NASA had always placed a strong bet that the public would be engaged by the idea of space as a place for us to work and eventually live. But after the success of Apollo, public interest and enthusiasm waned. It even waned during the program. A final 3 planned moon landings were scrapped. Also, most scientists thought that it was cheaper and less dangerous to create automated or robotic missions than to service them with astronauts. NASA's amazingly successful planetary missions from the 1970s to the 1990s were seen as evidence of the primacy of robotic spacecraft. Hubble was of course designed to be serviced by astronauts, but the often unanticipated problems they were able to solve in orbit, coupled with the positive public response and high TV ratings during the spacewalks, at least the early ones, persuaded many that the human presence was essential and inspirational. I'm going to look at the fun is just starting. Grandchildren. Your 30th is tomorrow. Yes, I heard about that. That's very exciting. Rookie. Oh, so cute. 3 grandchildren. That's so exciting. That's so nice. Lynn Jersey has longer to wait. But I heard Lynn Jersey's doing a little trip. When is that? Is that this weekend or are you going tomorrow? Did you go already? I'm not sure. But that's exciting. The 6-year-old wants to be an astronaut. Oh, that's so sweet. Good for them. Oh, the trip's postponed until June. Oh, no. Okay. Sad. Where was I? Oh, after the spacewalks. Yes. Okay. Oh, Merc got in the way. All right. So, more servicing missions followed. Each one rejuvenated the facility and kept it near the cutting edge of astronomy research. The second mission in 1997 installed a sensitive new spectrograph and Hubble's first instrument designed to work in the infrared. Astronauts also upgraded the archaic onboard computers. The third mission in 1999... I was trying to keep the yawn at bay and I couldn't do it. The third mission in 1999 was moved forward to deal with the vexing problem of failing gyros. Before the mission flew, the telescope lost a fourth gyro, essentially leaving it dead in the water. All 6 gyros were replaced, and the computer was upgraded to one with a blistering speed of 25 MHz and capacious 2 megabytes of RAM. That's 50 times slower and thousands of times less storage than the average smartphone. And this was written in 2010, I believe. This was published. 2013. So this was published in 2013, and even then, it was 50 times slower and thousands of times less storage than the average smartphone. And it's been 8 years. Oh my. The fourth mission in 2002 replaced the last of the original instruments and also removed CoStar, since it was no longer needed. Each subsequent instrument has had its optics designed to compensate for the aberration of the primary mirror. The infrared instrument was revived, having run out of coolant 2 years early. New and better solar arrays were installed, along with a new power system, which caused some anxiety since to install it, the telescope had to be completely powered down for the first time since launch. Except for its mirror, Hubble is reminiscent of the ship of Theseus, a story from antiquity where every plank and piece of wood of a ship is replaced as it plies the sea. The fifth and last servicing mission almost didn't happen. Once again, the mission was affected by a shuttle disaster, in this case, the catastrophic loss of Columbia and the crew in February 2003. NASA Administrator Sean O'Keefe decided that human repairs of the telescope were too risky, and future shuttle flights could only go to the safe harbor of the International Space Station. He also studied engineering reports and concluded that a robotic servicing mission was so difficult that it would most likely fail. At that point, Hubble was destined to die a natural death as gyros and data links failed. When in January 2004 it was announced that the Hubble Space Telescope would be scrapped, the public's response was overwhelmingly in support of refurbishing the instrument in orbit. David Dvorkin and Robert Smith report that a Save the Hubble movement sprang into life. Robert Zimmerman similarly comments, quote, "The public response was, to put it mildly, loud. Very soon, NASA was getting 400 emails a day in protest, and over the next few weeks, editorials and op-eds in dozens of newspapers across the United States came out against the decision." End quote. Zimmerman details the history, development, and deployment of the telescope, as well as its more significant findings. He suggests that Hubble, more than any other telescope or major scientific instrument, has allowed humankind to explore what lies at the furthest depths of space, and that this is the one reason for the widespread public sense of ownership. This is one reason for the widespread public sense of ownership in what some newspapers have called the People's Telescope. Not since Edwin Hubble did his pioneering work on cosmology with the 100-inch reflector at Mount Wilson Observatory has public interest in a particular instrument been so intense or pervasive. O'Keefe and other NASA officials were taken aback by the public response. They'd expected astronomers to lobby hard for another servicing mission, and they weren't surprised that astronauts weighed in, saying they'd signed up knowing the risks and they wanted to service the telescope. Sorry. But it turned out that a large number of people felt attached to Hubble, through its spectacular pictures and newsworthy discoveries. They felt clear affection for the facility, and since the taxpayer had indeed paid for it, the agency took notice, and O'Keefe first reevaluated and then reversed his decision. The fifth servicing mission went off without a hitch in May 2009, leaving the telescope in better shape overall and with certain capabilities 100 times more effective than its original configuration. 2 new instruments were installed, 2 others were fixed, and many other repairs were carried out since it was agreed by everyone that this was the last time the telescope would be serviced. And I have a picture of the telescope, which I feel like I should have shown earlier. But the books tell me to show it now, so I'm going to show it now. There she is. If you haven't seen Hubble before, there she is. And, yeah, this just says that Hubble Space Telescope is still in high demand as astronomy's flagship facility over 2 decades after it was launched. And the space shuttle missions were what saved it and what has kept it up to date. All right. So, Hubble's continual rejuvenation is a major part of its scientific impact. The instruments built for the telescope are state-of-the-art, and competition for time on the telescope has consistently been so intense that only 1 in 8 proposals get approved. All this comes with a hefty price tag. Estimating the cost of Hubble is difficult because of how much to assign to the shuttle launches and astronaut activities, but a 22-a-year price tag of $6 billion is probably not far from the mark. For reference, the budget was $400 million when construction started, and the cost at launch was $2.5 billion. Compared to slightly larger 4-meter telescopes on the ground, Hubble generates 15 times as many scientific citations, one crude measure of impact on a field, but costs 100 times as much to operate and maintain. Regardless of its cost, the facility sets a very high bar on any subsequent space telescope. As Malcolm Longair, Emeritus Professor of Physics at the University of Cambridge and former chairman of the Space Telescope Science Institute Council, has observed, quote, "The Hubble Space Telescope has undoubtedly had a greater public impact than any other space astronomy mission ever." End quote. He also notes that this small telescope's, quote, "images are not only beautiful, but are full of spectacular new science," end quote, much of which was unimagined by the astronomers who conceived and launched the instrument. That's the end of that section. Just gonna grab some water really quick. I like this chapter so far. I like Hubble. It's fun to learn about. I feel like a lot of the other chapters, except for some of the earlier ones, it's stuff that I know very, very little about. But this one, I know a lot about Hubble already. So it's like, oh, let's do a little bit more of a deep dive. It's fun. The People's Telescope. The Hubble Space Telescope has contributed to the identification of exoplanets, the dark energy that permeates the universe, and massive black holes that lurk in nearby galaxies. Probably no more science facility has left its mark in so many homes or done more to advance the general public's understanding of the structure, age, and size of the universe. Breathtaking photographs of regions of star formation, stunning spiral galaxies, exploding planetary nebula, and the most distant galaxies in the visible universe spill out of coffee table books, adorn the walls of children's bedrooms, and serve as computer screensavers. Why is that? The answer is not simply that the Hubble images pervade popular culture, though of course they do. There are multiple factors that might account for the telescope's tremendous popularity and an increasing public awareness of and affection for the telescope. While there are telescopes with 25 times the light-gathering power on Earth, Hubble remains the premier tool of astronomers due to its exquisite sensitivity, and the ubiquity of the Hubble photographs has been unprecedented. From newspapers and magazine covers to planetarium and museum programs and displays, popular science books, posters, calendars, and postage stamps, Hubble images pervade popular culture. Moreover, The emergence of the internet has afforded global access to the telescope's photos and scientific results. In July 1994, when comet Shoemaker-Levy 9 slammed into Jupiter with an estimated explosive force of 600 times humanity's entire nuclear arsenal, Hubble offered up-close views of the devastating planetary impacts. Astronomer David Levy, co-discoverer of the comet, reported that millions of people around the world watched on television or via the internet as the comet's line of fragments bombarded the massive planet. Art historian Elizabeth Kessler offers several less obvious reasons why the Hubble Space Telescope is so cherished worldwide. She contends that Hubble's spectacular images have become, quote, interwoven into our larger visual culture, in part because of their very deliberate construction along the lines of sublime art, which often seeks to evoke grandeur, great height and breadth of field, and an overwhelming awe of the power of nature. She points out that many of the Hubble images released by the Space Telescope Science Institute and the associated Hubble Heritage Project reflect the aesthetics of 19th century paintings of the American West. Quote, light streams from above, end quote, in the Hubble images, as in landscape paintings, explained Kessler, despite the fact that there is no up or down in space. Through such framing strategies, Hubble's photos are often configured like landscape paintings or photographs. Kessler argues that what also endears Hubble to so many is that its photos provide a means for public audiences to, quote, imagine the possibility of seeing such spacescapes with our own eyes, end quote. But Kessler is careful to clarify that all published Hubble photos are interpretations, usually composites of multiple images captured at various wavelengths of light. Even if we could travel at many times the speed of light across the galaxy to observe astrophysical objects, because of the rods and cones in the human eye, we would likely be unable to see color in the faint light sources. The reason is that the cones in the human eye allow us to see color, but cones need lots of light to do so. The rods require less light, but do not pick up color. That's why photographs of the Milky Way arced across the night sky often include color that we cannot see with the naked eye. Kessler points out that the Hubble heritage images are extensively processed and represent not what the human eye would see, quote, but a careful series of steps that translate numeric data into picture, end quote. Hubble collects data in visible light, but also supports a suite of instruments that see at wavelengths not visible to the human eye, such as infrared and ultraviolet light that can reveal additional details. In actuality, HST's electronic detectors see only intensity, which can be represented in grayscale, a range of shades of black and white, or gray. A set of filters made of colored glass, such as red, green, and blue, are rotated in front of the detector as images are captured. With spectroscopy, different wavelengths of light are dispersed with a grating and linearly arrayed on the detector. Once the data has been collected, color is added in processing by combining the images using different color filters with the appropriate weights to reproduce true color that can be used to distinguish gases within a nebula or their temperatures, or to distinguish young, hot, newly formed stars from older, cooler stars. That's the end of that section. You also think it's nice that we heard the person the scope was named for? Yeah. Yeah, I like that. Yeah, because, like, Hubble is, I feel like, yeah, Hubble is one of the most well-known of the, what's it called? People who spacecraft and different missions were named after. Yeah, which is pretty cool. Trying to think of other ones. It's kind of the main one. But, oh, thank you so much for sharing that. Yeah, this is great. So, Student McLeod just shared a link to the Hubble Heritage site. And it's just called, you can probably go to hubblesite.org, or you can just click on that link there. And it's it says the stated goal of the project was to use the Hubble Space Telescope's archive of imagery, augmented with new observation data, to produce aesthetically impactful and scientifically accurate color images of our universe. So the team has since disbanded, but the legacy of the program remains. And so you can go through and just like explore all these pictures, and there's some crazy ones, like you can see. Just beautiful stuff. So feel free to go check that out. Check it out while I'm reading. Go ahead. Do we want to become famous? Buy followers? Huh. I don't need to buy followers. Y'all are already here. Let's ban them. There we go. Thank you for the warning. Bye, spam. All right. But yeah, feel free to take a look at those pictures. They're gorgeous. I have a few that will come later in the chapter that I will show you guys some standout Hubble photos, but there's a lot. So, all right. The science in Hubble's iconic pictures. Kessler explains that some astronomers were initially dismissive of Hubble's pretty pictures. They felt such images had less to do with science, and that the public would accept the false color photos as what Hubble actually sees. But as Kessler points out, Hubble was the vehicle for changing this perception, particularly in the case of the stunning images of the Eagle Nebula, M16, released in 1995. There's actually not an image of that, but I want to find one, so it's probably on here. Let's see. Eagle. Show me the eagle. Show me the bird. Oh, yeah. Okay, this is the Pillars of Creation image, which I'm sure a lot of you guys have seen before, but I'm going to pull it up anyway because it's crazy. Let's open that image in a new tab. Hell yeah. Gorgeous. So this is the Eagle Nebula, M16, Pillars of Creation. Has a lot of names. But this is the image they are referring to, and I'm going to leave it up while I keep reading. A group of astronomers at Arizona State University, led by Jeff Hester, were interested in photoevaporation, by which they suggested radiation from a massive star in the nebula is evaporating gaseous material away from the sites of newly forming stars. Kessler notes that Hester's team, quote, did not plan the observation with the intention of creating a visually impressive picture, end quote. However, their remarkable image of the Eagle Nebula awed scientists and general audiences alike. And, as anticipated, in the nebula's 10 trillion kilometer gaseous columns, Hester's team identified regions of newly forming stars. Upon release of the Eagle Nebula images, Kessler reports, quote, the New York Times, Washington Post, USA Today, and other major newspapers printed articles featuring the image, and Newsweek, U.S. News and World Report, and Time all ran stories in the following weeks, end quote. Kessler highlights the fact that while the news reports detailed Hester's theory regarding new star formation, the real emphasis of the news coverage was the spectacular beauty of the cloud pillars in the Eagle Nebula, subsequently dubbed the Pillars of Creation. A report in 1999 on Hubble's popularity by the Space Telescope Science Institute indicates that, quote, web hits at the time of the M16 release were about 500,000 a month, end quote. The fascination with Hester's image of the Eagle Nebula demonstrated that stunning astronomical photos could capture both important scientific data and amazing spacescapes that readily communicate complex information to general audiences. Kessler points out that NASA quickly realized the tremendous public support for Hubble might be better served through an organization that would regularly request, produce, and release images taken by Hubble. The Hubble Heritage Project emerged out of such interest. It's a pretty picture. You're going to be looking at that Hubble. Yeah. You can very easily get lost in Hubble images. They're all so pretty. Jeff Hester took the famous Hubble image. Yeah, he writes for astronomy. That's cool. It's a great picture. I have a long quote from him, actually, too, right after this. So let's hear what he has to say. Commenting on what he and members of the Hubble Heritage Project were looking for in the composition of spectacular photos like that of the Eagle Nebula, Jeff Hester explains, quote, "I want people to realize, when they look at images like that what they are looking at is humans acting on this urge within us, going out there and proactively building the technology and the tools that allow us to reach out with our minds and our aesthetic and our imaginations and our sense of wonder and our sense of curiosity. That these photographs are not just nicely aesthetic, but testaments to what we as people are able to do. To take images of columns of clouds of gas and dust several thousand light years away in which stars are forming, and to bring them home and make them part of the universe known to us, to extend the sphere of human mind and imagination out to encompass those things." End quote. Hester nevertheless understands the difficulty in communicating complex science information. Quote, "Science demands a rigorous vocabulary, the vocabulary of mathematics. It demands that you learn to think in that vocabulary. It's not a vocabulary that's accessible to a lot of people. It really matters that you find a way to get around the vocabulary problem, that you find a way to bother to think about who it is that you're talking to, what it is that they are familiar with, so that instead they can start to get their arms around it a little bit." End quote. The Hubble Heritage Project's homepage provides thumbnails of approximately 200 images. These are the best of the best from among tens of thousands of images taken by the facility. According to Kessler, the project was the brainchild of planetary scientist Keith Noll and astronomer Howard Bond. Along with Ann Kinney and Carol Christian, these scientists collaborated to create Hubble Heritage images to promote public education and general interest in astronomy and space science. Kessler contends that they have expertly achieved these goals by blurring the boundaries between art and science to contribute to both astronomical investigation as well as popular understanding of cosmology. Keith Noll summarizes the project's objective. Quote, "My real hope for this is that there are kids that have our pictures on their walls, that maybe spend some time dreaming about what it's like to be in space, what it would be like to travel to these exotic places. But what I really hope is that they all sort of carry this little bit of awe and mystery with them in their lives, so that everything isn't just about getting up and driving in traffic and paying bills. It kind of helps to remember how amazing the universe is." End quote. Hubble's photos easily convey some of the most fascinating aspects of star birth and death, and solar system formation. In many cases, it doesn't require specialized or scientific training to immediately grasp the importance of some of Hubble's most remarkable images. This is true for the Hubble photos of the Eagle Nebula and its collapsing gases in the star birth regions, the newly forming star systems in the Orion Nebula, M42, with its protoplanetary disks the size of our solar system, the star birth visible in the arms of the Whirlpool Galaxy as illustrated in the mosaic of M51, or the bizarre and complex cloud formations produced by dying stars at the heart of planetary nebulae. And I have another picture for you guys that I will bring up while I keep reading. Gorgeous. I'm gonna try to zoom in a little bit. Okay, there we go. Beautiful. This is the M51 Whirlpool Galaxy that I just mentioned. And I'll leave that up so you can stare at it while I keep reading. Perhaps the simplest reason for the Hubble telescope being so cherished is that in a single bound, complex scientific investigations can be conveyed in a handful of amazing images. The tremendous energy radiated as stars blow off their gaseous outer layers is evident at a glance from a single image. While the average person may not have imagined the import of a star's magnetic field in shaping planetary nebulae, the effects of intense radiation and stellar winds are nearly palpable in such photographs. In images with less obvious information, a simple caption can make the meaning immediately comprehensible to the non-specialist. A short caption regarding the pillars of dust in the Eagle Nebula towering to 10 trillion kilometers, or 6 trillion miles, or explaining that stellar winds in the Red Spider Nebula, which I have a picture of as well. Let me switch to that picture. There we go. The Spider Nebula, otherwise known as NGC 6537. So explaining that stellar winds in this red spider nebula produce waves of dust and gas 100 billion kilometers high, while nearly incomprehensible, has afforded general audiences unprecedented understanding of the incredible energy and matter involved in star birth and death. Hubble images of gravitational lensing caused by large clusters of galaxies, majestic barred spirals whirling through space, and spectacular globular clusters have been indelibly etched into the public imagination. But beyond this popular appeal, the Hubble Space Telescope has generated enough unique data to qualify as the most successful scientific experiment in history. That's the end of that section. I don't know why they call this one the Spider Nebula. I mean, I guess it's got some arms. It just looks more like an X. Looks like something you see in a superhero movie. But it's still cool. I just you hear spider, you think, okay, 8 legs. Where's the other 4? It's still really cool, though. But yeah, these and more images can be found on the Hubble Heritage site. So, go check that out. All right. The cosmic distance scale. What does the science yield from this premier facility, and how has it changed our view of the universe? In the early years of a space telescope, there's often a concerted effort to put a lot of time into a few critical projects, so that major results will be obtained even if the telescope fails. There's understandable tension involved in this decision, since the Hubble has always been oversubscribed by a large factor, and it keeps more astronomers happy if the time is thinly spread among many projects. Riccardo Giacconi, the first director of the Space Telescope Science Institute, was persuaded to set aside substantial time for peer-reviewed key projects. Early in the history of this facility, 3 of these were approved. 2 of them were successful, but are not well known: a medium-deep survey of galaxies and a spectroscopic survey of quasars to probe the hot and diffuse gas in the intergalactic medium. But the 3rd is rightly considered one of Hubble Space Telescope's finest achievements. As we saw in the chapter on Hipparcos, distance is fundamental to astronomy, yet it's one of the hardest things to measure. In the everyday world, we judge distance based on familiarity with the size of a tree or a person, for example, or the brightness of a lamp or a streetlight. But in the universe, objects like stars and galaxies range over many orders of magnitude in size and brightness, so their apparent size or brightness is a very unreliable guide to distance. Is that a bright object far away or a dim object nearby? Is that a large object far away or a small object close by? This type of confusion is common. Considered in a different way, poorly determined distances limit our knowledge of how the universe works. Without knowing how far away an object is, we don't know its true size or its true brightness. That also means we don't know its mass or luminosity, which means we can't have a real physical understanding of something that's so remote that we'll never be able to study it in the lab or gather a sample of it. This urge to measure distances accurately becomes acute in the study of the universe as one entity. In an expanding universe, precise distances are needed to answer fundamental questions. What is the size of the universe, and how old is it? Early in the life of the Hubble telescope, hundreds of orbits were devoted to measuring distances to 36 galaxies. Fittingly, this key project used the method that Edwin Hubble had used in the early 1920s to show that the Andromeda Nebula was a remote stellar system. Hubble identified examples of a well-known class of variable stars in M31, the Cepheid variables. Cepheids pulsate in a well-understood and well-regulated way, and this behavior manifests as a linear relationship between the luminosity and their period of variation. By finding Cepheids in a remote galaxy and measuring their periods with a series of images taken over hundreds of days, the star's absolute and apparent brightness can be combined to derive the distance. Cepheids are very luminous and can be seen to large distances. but they're buried in dense regions of overlapping star images, so the sharp imaging of a telescope in space is needed to pick them out. Wendy Friedman, Rob Kennicott, and Jeremy Mould lead the project, accompanied by 25 other astronomers from around the world. The Key project had a goal of measuring the distance scale to an accuracy of 10%. This might seem unduly modest, but it's a reflection of the difficulty of the experiment. In the decade leading up to the launch of Hubble, astronomers had disagreed by 50% or more on the distance scale. In particular, the goal was to measure a quantity called the Hubble constant to within 10%. The Hubble constant is the current expansion rate of the universe, measured in units of kilometers per second per megaparsec. Hubble discovered a linear relation between the distance and the recession velocity of a galaxy. The Hubble constant sets that scaling. So if the Hubble constant is 70, then for every megaparsec, 3.3 million light years, increase in distance, the recession velocity increases by 70 kilometers per second, or 157,000 miles per hour. On average, this scaling says that a galaxy a million light years away is receding from the Milky Way at 47,000 miles per hour. A galaxy 10 million light years away is receding at 470 miles per hour, 470,000 miles per hour, and so on. Inverting the Hubble constant allows us to project the expansion back to zero separation of all galaxies, and so gives us a good estimate of the age of the universe. By measuring distances out to 20 megaparsecs, or 66 million light years, the Key project would determine the size, expansion rate, and age of the universe. The formal result of the Key project was the measurement of a current expansion rate of 73 kilometers per second per megaparsec, with a random error of 6 and a systematic error of 8, published in the 28th paper in the series from team members, which indicates just how productive and prolific one Hubble project can be. Syncing the distance scale in this way has been a foundation stone in the emergence of precision cosmology, where overall attributes of the universe are becoming very well determined. Although the Key project worked in our cosmic backyard, or the local 0.01% of the visible universe, it leveraged and helped to improve distance measurements both inward and outward. Hubble also was able to measure parallaxes for Cepheids in the Milky Way, along with Hipparcos, which we've previously mentioned, and tether the distance scale in direct geometric measures. Knowing Cepheid distances for several dozen galaxies calibrated the use of other types of distance indicators, such as supernovae and the well-defined rotation of properties of galaxies, which can be used out in the remote universe. That's the end of that section. And here's my obligatory, let's flip through the chapter and see how many more pages we have. Okay. I think we're doing good. Gonna have some more water. Is anyone doing anything for Memorial Day this weekend? I kind of asked that before, but still curious. I live at the beach, and I am not going to the beach for Memorial Day. I'm actually going away from the beach to the desert. Oh, hello. Hello, brother. All right. Dark force. The Hubble Space Telescope has touched every area of astronomy, but some of its key contributions have profoundly shaped our view of the universe. One of the original hopes for the Hubble was to extend the Key project, which measured the local or current expansion rate, and measured the entire expansion history of the universe over cosmic time. Hubble's sensitivity and resolution allow it to observe supernovae in distant galaxies. A Type 1a supernova is a white dwarf star that detonates as a result of mass steadily siphoning onto it from a massive companion star. When the white dwarf exceeds the Chandrasekhar limit, which we encountered in the last chapter, it collapses and then explodes as a supernova. This well-regulated process means it's a standard bomb, with an intrinsic brightness that doesn't vary from one supernova to another by more than 15%. At peak brightness, the supernova rivals its parent galaxy in brightness. So these explosions can be seen to distances of 10 billion light years or more. And I have a picture of one of those. Here we go. So this is an image from, a series of images from Hubble. And these are some supernovae that are like billions of light years away. And it says when they die, these stars rival the brightness of their surrounding galaxies, enabling the distances to those galaxies to be measured. So essentially the whole thing is these specific type of supernovae are always going to be in a very specific range of brightness. And because they can, detect these and know what range of brightness they are, they can use that to figure out like, okay, well, this one looks darker than this one, so that must mean it's farther away because they should be about the same brightness. And that's how we figure out how far away galaxies are, which is pretty cool. Many of the heritage images would make nice wallpapers for laptops. Yeah, and also the great thing about that website is all of that stuff is totally free use because it's NASA images, and all of their stuff is in the public domain. So you can go and they've got super high res images. You could print one of those out and make it a poster on your wall or something if you wanted to. But yeah, they're great. In the mid-1990s, two groups studying supernovae saw something utterly unexpected. In an expanding universe, the effect of normal matter and dark matter is to slow down the expansion rate. By looking back in time with more and more distant supernovae, these researchers had expected to see supernovae appearing slightly brighter than expected for a constant expansion rate. The reasoning is that deceleration reduces the distance between us and a supernova relative to constant expansion, making it appear brighter. Instead, they saw the opposite effect. The distant supernovae were dimmer than expected. The interpretation was the distance to the dying star was larger than expected. Rather than decelerating, the universe has been accelerating. Cosmic acceleration is a very puzzling effect, because it implies a force acting in opposition to gravity. No such force is known in physics, so the cause of the phenomenon was called dark energy, where that phrase is really just a placeholder for ignorance. Dark energy seems to have the character of the cosmological constant, the term that Einstein added to the solutions of his equations of general relativity to suppress natural expansion, and which he later called the greatest blunder of his life. It's new and fundamental physics. The discovery of cosmic acceleration was based on images and spectra taken with ground-based telescopes. The Hubble Space Telescope didn't make the initial discovery, but confirming the result, extending the measurements to higher redshift, and putting constraints on the nature of dark energy, all of those have been essential contributions. Hubble's depth has been used to trace the expansion history back over 2/3 of the age of the universe. The data show that acceleration reverts to deceleration more than 5 billion years ago. Astronomers can now apportion the two major components of the universe, dark matter and dark energy. Dark energy accounts for 68%, dark matter accounts for 27%. Diffuse and hot gas in the intergalactic space is about 4.5%, and all the stars in all of the galaxies in the observable universe amount to only 0.4% of the cosmic pie. Dark forces govern the universe. Imagine the expanding universe with a brake and an accelerator. The driver isn't very competent, so they press both pedals at the same time. Dark matter is the brake because gravity slows the expansion. Dark energy is the accelerator. In the first 2/3 of the expansion history, the dark matter dominates and the expansion slows with time. But the effect of dark matter weakens because the density and the gravity force go down, while dark energy has a constant strength in both time and space. So the pressure on the brake eases while the accelerator is pressed the same amount. And about 5 billion years ago, all galaxies started to separate at ever-increasing rates. Some cosmologists consider it an unexplained coincidence that dark energy and dark matter, two mysterious entities with fundamentally different behavior, happen to have roughly the same strength and crossed paths relatively recently in cosmic time. This is the only time in cosmic history they are close to equal strength. For most of the early history of the universe, dark matter was utterly dominant, and forever into the future, dark energy will dominate. This coincidence only sharpens the enigma. That's the end of that section. Yeah, the download pictures. Yeah, they got the whole thing. It's like all set, ready to go. Oh, you could download like little versions of them if you don't have a great internet connection or something and just want to see them quick. Or you can download the really big ones and really get to like zoom in on them. It's great. All right. Dark force redux. Hubble has weighed in on the other major ingredients of the universe, dark matter. The existence of dark matter was first indicated in an observation of the Coma cluster of galaxies by the maverick Caltech astronomer Fritz Zwicky. Zwicky measured redshifts, or radial velocities, for galaxies in the cluster and saw velocities that were much higher than anticipated. The galaxies were buzzing around like angry bees at over 500 kilometers per second, over 1 million miles per hour. If the cluster had the mass indicated by the stars in all the galaxies, it wasn't enough to keep those galaxies bound in one It wasn't enough to keep those galaxies bound in one region of space. In fact, visible mass was insufficient by a factor of 10. The Coma cluster should be flying apart, but it's not. So Zwicky hypothesized an invisible form of matter to hold it together. It had to be a form of matter that exerted gravity, but didn't radiate light or even interact with radiation. Dark matter. This observation was so odd and so unexpected that most astronomers simply set it aside. It didn't help that Zwicky was brilliant, but extremely cantankerous, and he made a lot of enemies in the profession with his blunt and often rude comments. But in the 1970s, the rotation of spiral galaxies also indicated unseen forms of matter extending far beyond the visible stars. Astronomers revisited Zwicky's observation and found that it was correct, and that other clusters of galaxies showed the same effect. Dark matter was a ubiquitous feature of the universe, on galactic scales and beyond galaxies in the space between them. The Hubble Space Telescope has cemented the measurement of dark matter in a very elegant way. Einstein's theory of general relativity says that mass bends light, and this prediction was confirmed in 1919, with starlight bending around the limb of the sun during a solar eclipse. We've seen that both Cassini and Hipparchus had a hand in showing that relativity was correct. Zwicky realized that a galaxy could bend light by a detectable amount, and he urged astronomers to search for that effect. Lensing was finally seen for the first time 5 years after Zwicky died, when the twin image mirage of a single quasar was observed in 1979. In the mid-1980s, the phenomenon of lensed arcs was discovered with 4-meter telescopes on the ground. Each lensed arc is an image of a galaxy behind a rich cluster, magnified and distorted by the cluster. Cluster lensing has a very particular signature because the arcs are fragments of concentric circles centered on the cluster core. The beautiful part of the effect is that the gravitational deflection is sensitive to all mass, light or dark, so it's a reliable way to weigh a cluster. Hubble's exquisite imaging has been used to study lensed arcs in dozens of clusters. Each background galaxy that gets imaged is a little experiment in gravitational optics and a confirmation of general relativity. In some clusters, there are hundreds of little arcs, so the mass measurement of the cluster is very reliable. It's like having an optics experiment with hundreds of light rays. And I have a picture of this for you guys that I will put up while I keep reading. Here it is. This is the cluster of galaxies Able 2218 that acts as a gravitational lens, where it's visible and dark matter distort and amplify the light of more distant background galaxies. All right. The observations clinch the fact that dark matter exceeds normal matter by a factor of 6, or the ratio of the 27% to 4.5% contributions mentioned earlier. They also allow the dark matter to be mapped in the cluster, and the spatial distribution is critical information in helping decide the physical nature of this universal but mysterious substance. Here we go. Hubble has also played a pivotal role in locating a large type of dark object, massive black holes. Since the discovery of quasars in the 1960s, it has been clear that only a gravitational engine could generate so much energy from such a small volume. The energy source for quasars is thought to be a supermassive black hole, billions of times more massive than the Sun. As we saw in the last chapter, black holes aren't always black. Nothing can escape from the event horizon, but a black hole will gather hot gas into a rotating disk around it. The disk siphons material into the black hole, while the poles of the spinning black hole act as giant particle accelerators. The accretion disk emits huge amounts of ultraviolet and X-ray radiation, while the jets emit radio waves. For a long time, astronomers thought that the galaxies surrounding the quasars were special because they housed such a black hole. Over the last 15 years, Hubble has used its spectrographs to study stellar velocities near the centers of apparently normal galaxies near the Milky Way. Often, the data showed a sharp rise in star velocities near the nucleus of the galaxy. Calculating the density of matter that would generate such high velocities in such a small volume, the only possible explanation was an efficient gravitational engine, a black hole. But these black holes were surprising in two ways. First, they weren't as massive as the black holes that powered quasars. They ranged from 10 million to a few 100 million times the mass of the Sun. Second, the galaxies otherwise looked completely normal. Apparently, these black holes weren't active even though there was plenty of food or gaseous fuel in the center of these galaxies. As the data accumulated, it became clear that every galaxy has a black hole, with mass proportional to the mass of old stars in the galaxy. But those black holes must only be active a small fraction of the time and inert the rest of the time. This result has led to a paradigm shift in extragalactic astronomy. There's no division between normal and active galaxies. All galaxies are active at some level, but not all the time. Black holes are a standard component of a galaxy. There are a few intermediate mass black holes residing in globular clusters and in dwarf galaxies, filling in the mass range from 1,000 to 1,000,000 solar masses. Nature knows how to make black holes spanning a factor of 1,000,000,000 in mass. The low end of the range is collapsed stellar corpses the size of a city, and the high end is behemoths in galaxies 10 times larger than the Milky Way. Moreover, in their active phases, black holes eject mass and quench star formation and generally alter the properties of the surrounding galaxy. The co-evolution of galaxies and black holes is now a major field of research. With its exquisite resolution and sensitivity, Hubble is playing a big role. Sometime in the first 100 million years or so after the Big Bang, the first stars and galaxies formed, and black holes began to grow at the same time. That's the end of that section. Just checking to see. I shockingly don't have work after this. Unfortunately, I do have to go to the dentist after this. Oh, fun. Anyone get a cavity filled recently? Know how long that's going to take? Because I don't. I've only ever had like one cavity filled and they did it really fast. They were like, oh, we'll just do it with a laser. And I was like, okay. But I have some cavities. And they're little ones. They're not big ones. But they're like, we need to fix these before they get bigger. And I'm like, okay, I'll do it. But I'm like, how long is that going to take? Is it going to hurt? It's probably going to hurt, right? I don't know. I know they stick a needle in your mouth, and I'm not excited about that. Not hype. I'm wondering, I'm like, do you think they'll let me, like, listen to, like, music while I do it? Like, just have headphones in, and then they, like, keep my eyes closed, and if they need me, they just kind of, like, poke me and be like, hey, spit or something, you know? Like... All right. Rather me than you guys. Yeah, fair enough. Keep my eyes closed. Okay. Yeah, I just don't want to see that. I feel like everything else I'll be fine. I just don't want to see the needle. Because I know they like numb your gums before they like do the little stabby stab. But like, I don't know. Maybe they don't do that anymore. I don't know. I was a child the last time I had like any sort of thing like that. So maybe they just force the needle and they're like, you can deal with it. You're an adult now. Deal with the pain. I don't know. We'll see. Anyway, this is very off topic. The deepest picture ever taken. To learn how galaxies formed, astronomers took their best facility and pushed it to the limit. The result was the deepest picture of the sky ever made. The Hubble Ultra Deep Field had its genesis in an earlier project called the Hubble Deep Field, and a bold decision by the second director of the Space Telescope Science Institute, Bob Williams. In 1995, Williams devoted the 10% of the observing time that he had at his discretion as director to a very deep multicolor image of a single patch of sky. To see why this was bold, let's take a brief excursion into the culture and sociology of research astronomy. For astronomers, the Hubble Space Telescope is the best game in town. The Hubble has made more discoveries and generated more papers than any other research facility. Every year, astronomers craft proposals for time, and there are many times more proposals than can get on the telescope. There's a natural tendency to spread the bets. Directors had used their discretionary time similarly, giving most of it to small proposals to ease the oversubscription. Williams decided to put all his eggs in one basket by devoting 150 orbits, a huge allocation of time, to a single deep image. His decision changed the culture of astronomy. He let the research community decide where the telescope should be pointed for those 140 hours, and what color of filter should be used, but he insisted that the data be processed and made public immediately for any astronomer to use. The tiny region chosen in Ursa Major, 1/28 millionth of the sky, contained over 3,000 galaxies, and the data paper for the Hubble Deep Field has been cited over 1,000 times by other research papers. Also, this large investment of a scarce resource in one field persuaded infrared, radio, and X-ray astronomers to follow suit. Other leading telescopes put copious time into complementing the optical images with data across the electromagnetic spectrum, and in many cases, those data were also made available quickly. An intriguing mix of competition and altruism spurred the research forward. But what if the one field you pick isn't typical for some reason? A premise of cosmology is that our location isn't special or unusual. This assumption is called the cosmological principle. In practice, it means showing that the universe is homogeneous and isotropic. Homogeneous means roughly the same at all locations, which is hard to prove since we can't travel beyond the galaxy in a spaceship. Isotropic means the same in all directions. While there's been no indication that we see different numbers and types of galaxies looking in one direction in the universe compared to any other, astronomers were nervous. So Bob Williams committed additional Hubble time to a small deep field in the southern sky in 2000. Since then, deep fields have sprouted like mushrooms. When a new sensitive camera was installed during the fourth servicing mission in 2002, the Space Telescope Institute director at the time, Steve Beckwith, upped the ante by putting 400 orbits, 1,000,000 seconds of observing time distributed in 4 colors, into a tiny patch of sky in the direction of the Fornax constellation. That's the Hubble Ultra Deep Field. The most distant light in this image has taken 95% of the age of the universe to reach us, so it comes from close to the dawn of light. To get a sense of this incredible image, hold a pin out at arm's length. The head of the pin covers as much sky as the image produced by Hubble's CCD camera. Astronomers harvested 10,000 galaxies from this minuscule bit of the sky. The faintest are 5 billion times fainter than the eye can see, and Hubble can only collect 1 photon per minute from them. Think of trying to see a firefly on the moon. Surveying the entire sky to this depth would take 1,000,000 years of uninterrupted observing. The numbers are staggering. and they can be used to derive some important information about the contents of the universe. Since the ultra-deep field covers 1/13 millionth of the sky, the projected total number of galaxies in all directions is 130 billion. Each galaxy will on average contain 400 billion stars. So there are about 10 to the 23rd stars in the visible universe, or 100,000 billion. That's a mind-bending number. But the real excitement comes from the implications for life. We've learned that planets are ubiquitous around sun-like stars, and expect to know soon about the abundance of habitable and Earth-like planets. The number of potential biological experiments in this universe may not be very different from the number of stars. What odds would you put on us being alone? When you look at the faint galaxies littering these deep fields, mere smudges of ancient light, it's irresistible to imagine that in many of them, or even all of them, someone or something is looking across the canyons of time and space back at you. That's the end of that section. Getting a phone call. But it's not from LA, so I'm going to go with it's probably spam. I'm going to show you guys the Hubble Deep Field, because we talked about it and I didn't have an image of it. So if you guys haven't seen it before, the Hubble, that's the Ultra. I want the regular Deep Field. Show me the normal one. Okay, I can only find the ultra deep field, which, I mean, it's cool. So I'll show you that one. But this is the... Oh, wait, that zoomed in too much. Oh, I guess it's not. Okay. This is the Hubble Ultra Deep Field. So this is the second one they did. It's very cool. And, yeah, so this is like, all of these are galaxies, which is amazing. These ones are really cool. So these are some of the closer ones. Yeah, it's amazing. Oh, some advice for my dentist appointment. Thank you. I will let them know. Black holes can be studied. I don't know. We can kind of study the outside of black holes and what they're doing to their like binary stars and stuff like that. But I mean, we can't really look into one or anything like that. You know, a lot of it is hypothesis. We can image them now, though. That's exciting. What do you say? The dawn of light. Just wrap your head around that. I know, right? It's crazy. Yeah, it's gorgeous. You downloaded a feeding black hole from Galix for desktop wallpaper. Nice. Space provides some really great desktop backgrounds. It provides a lot of other things as well. That's probably one of the most boring things that it provides, but they're gorgeous. Or not boring, but like the most that is the most simplified way you can talk about space. It's like, yeah, space is pretty. It makes nice desktop backgrounds, which is funny. Oh, CERN jerky focus. Nice. All right. Characterizing distant worlds. Closer to home, astronomers have grown confident that there are habitable worlds in our galactic neighborhood as they harvest exoplanets and begin to detect objects close to the Earth in mass. The Hubble Space Telescope wasn't in on the ground floor of the discovery of planets beyond the solar system. That was the work of ground-based observers patiently working on small telescopes for decades. However, it has played a central role in going beyond detection to begin to characterize the planets. With more than 1,000 exoplanets confirmed, and dozens more being discovered every week, the thrill of discovery is not what it was in the late 1990s. Almost all of these planets have been discovered by an indirect method, where the influence of an orbiting planet is seen in a periodic Doppler shift of the parent star. No one doubts that these planets are real, but the evidence of seeing the planet is more direct. So it was very exciting when Hubble provided the first optical image of an exoplanet in 2008. A planet 3 times Jupiter's mass is orbiting the bright star Fomalhaut, 25 light-years away. The planet is embedded in a dust disk of the young star and was spotted in archival images taken for a different purpose at 2 different epochs. Another research team has developed special imaging processing techniques that may be able to dig as many as 100 new exoplanets out of the vast trove of Hubble archival images. One of the many surprises in exoplanet research was the existence of hot Jupiters, planets like one of the giant planets in our solar system, but orbiting closer to their stars than Mercury does to the Sun. These planets present an opportunity because the chances of an alignment that lead to an eclipse, as seen from the Earth, greatly increase. Over 100 exoplanets have been seen to eclipse their parent star, dimming it slightly for a few hours. These events are repeatable, and Hubble has observed several exoplanet eclipses with its spectrographs. The spectrum of the star shows absorption from a trace amount of heavy elements, but when the transit occurs, some starlight filters through the atmosphere of the gas giant, and an extra imprint of absorption is added to the spectrum from ingredients in the planet atmosphere. So far, sodium, oxygen, carbon, and hydrogen were detected in the atmosphere of one planet, and carbon dioxide, methane, and water, or rather steam, in the atmosphere of another. Both are Jupiter-sized and far too hot to be habitable, but these observations are showing the path for the detection of biomarkers, the chemical imprints of biology in the atmosphere of an exoplanet. This may well be the way we first discover life beyond Earth. Finally, Hubble has contributed to the statistical understanding of exoplanets. Looking toward the crowded stellar bulge of the Milky Way, 26,000 light-years away, the telescope found 16 exoplanet candidates orbiting a variety of stars. 5 of the planets are in an extreme category not yet found by any other search method: super rapid orbiters that whirl around their stars in less than a day. They were discovered in 2006 using the transit method. Extrapolating to the entire galaxy, the survey projects to 6 billion Jupiter-sized planets in the Milky Way. Theory predicts terrestrial planets in roughly equal or greater numbers than giant planets, so the distant worlds are out there, just waiting for us to reel them in. Make sure your black hole wallpaper doesn't suck you in. Completing Hubble's work. The Hubble Deep Field and the Ultra Deep Field images would have fascinated Edwin Hubble perhaps most of all, since they plumb the depths of space near the edge of the observable universe and reveal our universe as it was 400 million years after the Big Bang. In current cosmological models based on the Big Bang, the universe has an edge in time rather than space. Looking out, we look back in time due to the finite speed of light. At the limits of Hubble's vision, no edge in space has been detected. Rather, we've looked so far back in cosmic time that we're seeing the epoch where the first small galaxies were created and began merging into the larger and mature galaxies we see around us now. The edge in time corresponds to first light, but beyond that was an early period called the Dark Ages, when there were no stars and galaxies. Hubble has been so successful that it has almost completed the fundamental task of seeing the entire population of galaxies in the visible universe over all cosmic time. The ultra-deep field images provide new information regarding how highly structured spiral galaxies are formed. Astronomers now understand that large spiral galaxies represent mergers over eons of fragments of the young, chaotic galaxies seen at the faintest levels of brightness. Quote, "To some degree, we can follow the stages of galaxy formation right into the fog bank of the Dark Ages and beyond, even toward the Big Bang itself," writes Jeff Canopy, who describes the Hubble Space Telescope, quote, "as both a pathfinder and a plumb line into the vast depths of our cosmic origins," end quote. The deep field images represent humankind's first glimpse of those origins. The Hubble Space Telescope is named in recognition of Edwin Hubble, an observational astronomer who in the 1920s and 1930s worked at Mount Wilson Observatory with the Hooker 100-inch telescope, then the largest reflecting telescope in the world. During his lifetime, Hubble was accepted as the world's preeminent observational astronomer, in part because the 100-inch reflector allowed Hubble to seek answers to some of the then fundamental questions of astronomy. Whether there were galaxies beyond the Milky Way, how to create an accurate distance ladder to such galaxies, and what could be known as the limits of the observable universe. In 1923, Hubble determined a distance to the Andromeda Galaxy of roughly 800,000 light-years. Though today we know it lies about 2.2 to 2.3 million light-years from our galaxy, Hubble's calculation settled once and for all the debate over whether anything existed beyond the Milky Way galaxy. It was a monumental find. Hubble accomplished this through Henrietta Leavitt's research into the regular periodices of Cepheid variable stars. Upon discovering and charting a Cepheid variable in Andromeda, Edwin Hubble could determine its intrinsic brightness to calculate a distance to the galaxy. Later, in 1929, he used the 100-inch reflector and the inestimable skills of Milton Humason, as an observer and photographer, to determine that galaxies are racing away from each other at remarkable speeds. Hubble didn't use the phrase when he published his result, but this marked the discovery of the expanding universe. Perhaps it was Grace, Edwin Hubble's wife, who dubbed him the Mariner of the Nebulae. She was an eloquent writer whose memories of Hubble are archived at the Huntington Library in San Marino, California. Gail Christensen's biography, which draws upon Grace's unpublished memoirs of Hubble, vividly recreates the scene of the astronomer at work at his telescope. Quote, "Like a captain on the bridge of a great ship, the master mariner barked out his orders. So many hours and so many degrees. Then came the metallic whining of the traverse, a series of loud clicks, a final heavy clang of the Victorian machinery as the 100-inch was clamped," end quote, into place for viewing far-flung galaxies, or nebulae as Hubble referred to them. Christensen extends the metaphor, characterizing Hubble as a sentinel mariner, quote, "slipping night after night, silent and alone, past the distant shoals of the nebulae," end quote. Hubble himself wrote of the astronomical exploration in terms of oceanic exploration. He spoke of the 100-inch reflecting telescope as performing reconnaissance at the, quote, "dim boundary, the utmost limits of our telescopes," as Hubble in the cold early morning hours would, quote, "search among ghostly errors of measurement for landmarks that are scarcely more substantial," end quote. And that's the end of that section. Looks like we just have a couple more pages left. Hello, Remus Romania. Welcome. What happened in the... Yeah, it happened in the Scooby-Doo Cyber Chase movie, yeah. This is such a good movie. I love Scooby-Doo. I'm a big animation fan. A big fan of Scooby-Doo. Good stuff, good stuff. It has been a long odyssey for Hubble. I like the seafaring reference. Very nice. All right, let's finish this up. Cosmic voyages. The characterization of Edwin Hubble maneuvering the 100-inch reflector like a mariner upon a vast sea evokes another celebrated captain who navigated the depths of space in the science fiction television series Star Trek, launched in September 1966. As noted in the chapter on the Voyager mission, Captain James T. Kirk of the Starship Enterprise, portrayed by William Shatner, commanded a fictional 5-year mission to explore the far reaches of our galaxy. When Gene Roddenberry began producing Star Trek, the world's attention was turned towards space as the final frontier, and the dream of traveling vast distances across our galaxy was at a fever pitch. The Apollo missions of the late 1960s and early 1970s captivated audiences around the world who watched with trepidation as Neil Armstrong, and through him humankind, stepped onto the surface of another world for the first time. We delighted in watching the astronauts skipping and hopping across the lunar surface, and bounding lazily over cratered terrain in the lunar rover. The final episode of the original Star Trek series was broadcast in June 1969, just a month before Neil Armstrong and Buzz Aldrin stood on the lunar surface. Many in that generation came away from the truncated Apollo program wistful that the limits of money and politics prevented NASA from further manned lunar exploration. One effect of Star Trek first airing in the run-up to the moon landing was that the series inspired the first spacefaring generation, including many at NASA. William Shatner writes of the original series that, quote, "Every time NASA launched a manned rocket, our ratings went up, meaning that people were very interested in space. And when our ratings went up, Congress voted more money for the space program." End quote. Even if we don't assign causation, this is interesting. The perceived interconnection between Star Trek and NASA extended to NASA itself. Shatner recalls, quote, "NASA officials often invited us to launches, and finally I decided to go to one of them. They treated me as space royalty, eventually allowing me to sit in the LEM, the moon landing module, with an astronaut. I was lying in the hammock like seats, looking out of the small windows at the universe displayed as the astronauts would see it. The astronaut who was teaching me how to fly the craft told me to look at a certain section of the star system, and as I did, flying beautifully across the entire horizon, came the Starship Enterprise." End quote. That model of the Enterprise was assembled, Shatner points out, by some of the same engineers who built the Apollo spacecraft that landed on the moon. So compelling was Roddenberry's vision that in the late 1970s, the space agency recruited Nichelle Nichols, who played Communications Officer Lieutenant Uhura in the original series, to help in attracting young people to NASA's program. In 1977, NASA had received roughly 1,600 applications for new hires, but fewer than 100 from women, and far fewer from minorities. Within 4 months of Nichols' recruiting, applications rocketed up to 8,400, with approximately 1,650 from women and 1,000 from minority candidates. Years later, in 1992, during the STS-47 mission, Space Shuttle astronaut Mae Jemison, the first African-American woman in space, made it her practice, in honor of Nichelle Nichols, to begin each of her shifts with, quote, "Hailing frequencies open," an often scripted line for Nichols. That same year, in 1992, in recognition of Star Trek's contribution to the popular fascination with space exploration, a portion of Roddenberry's ashes were flown aboard Space Shuttle Columbia. Fred Hoyle predicted over 60 years ago that when, quote, "the sheer isolation of the Earth had become plain to every man, whatever his nationality or creed, a new idea as powerful as any in history will be let loose," end quote. Hoyle optimistically expected, quote, "this not-so-distant development may well be for the good, as it must increasingly have the effect of exposing the futility of nationalistic strife, and would inevitably reconfigure the whole organization of society," end quote. Hoyle's point about a new understanding of Earth in the context of the vastness of space is in part why Star Trek and, later, the Hubble Space Telescope garnered such global interest. Both NASA and Star Trek contributed to a deep cultural narrative about the possibilities of exploring the universe through international collaboration. Only 24 men traveled to the moon, but unimaginable surveys of deep space have been realized via the Hubble Space Telescope. The telescope continues to capture and convey stunning images of galaxies and nebula, and inspire a new generation whose dreams of a time when not only a handful of carefully selected astronauts, but they themselves can explore worlds within our galaxy and beyond. That powerful cultural dream has been realized, as Hubble's cameras extend our vision to the very limits of the observable universe. When the Apollo 8 astronauts toured the world upon returning from the moon, Command Module pilot Michael Collins recalls that regardless of which nations they visited, people congratulated them on the fact that we, humankind, made it to the moon. Collins noted that people around the world embraced the moon landing as a collective human achievement. The Hubble Space Telescope, an international effort between NASA and the European Space Agency, is similarly embraced and loved globally as a shared human achievement. Hubble's remarkable images have forever altered our understanding of the cosmos and demonstrate how far humankind has reached across the universe in our as yet most palpable survey of the intergalactic abyss. And that's the end of that chapter. A very fitting end for the chapter on Hubble. Oh, and beautiful image of the Starship Enterprise, if you don't know it. This is an illustration, yeah. It's gorgeous. Yeah, I remember that. I mean, well, I don't remember that. I wasn't around for it. But I remember reading about Nichelle Nichols. She thought about leaving the show, and Martin Luther King Jr. asked her to stay, which was really nice. And so she did. She's great. The whole early cast is great. Let's find a picture of her. How's she doing? She's doing great. She's 88 years old. Here she is in the whole getup. She was Lieutenant Uhura. She's great. Everybody should go watch the original series Star Trek. It's so good. I don't know where it's available, but maybe it's still on Netflix. I'm not sure. It was on Netflix a while ago. But yeah, it was a fun chapter to read. I hope you guys enjoyed it. Hubble's always interesting to learn about. I think it's really cool. But I think that is pretty much it for this stream. Just going through all my tabs that I have open. I'm glad you enjoyed it. Yeah, bless her. She's excellent. She's doing well. She is 88, and I hope she lives for much longer. Yeah. But yeah, so I think we're gonna wrap it up right there. As far as the rest of the week goes, we have astronomy news on Wednesday. We have amateur astronomy on Friday. And then next week, I actually am not going to be here. I'm going to be driving back from Tucson on Monday. So next week, we're taking a break from Bookstream. And then I think, what's the schedule? Let's see. After that, we're keeping the 9 a.m. time, by the way. So I hope this works for everyone. It seems like it works for a good amount of you guys. But yeah, so we're skipping next week, and then we'll be back on the 7th with the WMAP chapter. And then after that, it's going to be the last chapter on the 14th. So I will talk to Professor Impey. Hopefully we'll be able to do a book stream, or like an author chat, on the 21st with him. So mark your calendars, I guess. And then we'll figure out what we do after that. So yeah. Oh, I'm glad you enjoyed your favorite stream. Oh, thank you so much. Good luck with the dentist. Thank you. Is it true that there's a problem with determining whether the speed of light is a constant or not? I don't think so. I'm pretty sure we're pretty confident on the speed of light. I know there was something recently, or maybe it was recently, maybe it was a while ago. I can't actually remember. But if the dentist hurts, you'll smack him. Oh, thanks. But I'm pretty sure the speed of light is a pretty fixed constant. I don't know if we've definitely done experiments on the speed of light. I think it's a proven universal constant, though. Yeah. But yeah, oh, Scooby-Doo thing? Oh, it's the Scooby-Doo theme song. Hell yeah. Very nice. All right, well, on that note, I'm going to leave you guys. I will see you on a Wednesday for astronomy news. Oh, be sure to follow and subscribe if you are so inclined. We are really close to 1,000 followers. We are at 981 right now. And once we hit that 1,000, we are going to schedule a special stream. We're going to do a bunch of stuff, and there's going to be a book giveaway and some other fun things. So be sure to follow if you haven't yet. Tell your friends. And what is this?
Getting to net.
Why no one's measured the speed of light? Well, yeah, it's hard to measure it, but it's been essentially physically proven through like theory and stuff and math. But we can talk more about that on Wednesday because then Michael will be here and he can talk about how he learned in class of something or other about the speed of light. So, all right, I'll see you guys later. Bye.